Hello and welcome in our systems programming practical course. I'm Anatol and I will be giving you today's lecture on kernel and system calls. So in this lecture we will learn about the different organization of kernels, the different execution levels of CPU instructions, and system calls, which are basically the interface between the kernel and the user space code. First, the kernel is the core component of the computer system. It's basically the first program that boots up with your computer, and it's the program that will manage the resources for every other program on the system. It will manage the memory for every application, manage physical threads, and how the different applications can use the I/O devices like hard disk. It also facilitates the communication between different applications through inter-process communications. And it is executed in a privileged mode to give complete control over everything. So this is the most privileged mode of the CPU instructions, and various different kernel designs will define different boundaries between the privileged and unprivileged mode. So as you can understand, different trade-offs between having more code in privileged mode and less reliability, and more code in unprivileged mode and less performance. First, the monolithic kernels is a design where all operating system services live inside kernel mode in a single address space, which means single binary, and different modules can be added at runtime. This is, for instance, the design of Linux or the different BSD variants. Also MS-DOS used this design. So as you can see in the diagram, the user mode is only running the application, and the operating system fully runs in kernel mode, and all the different components of the operating system are inside the same single address space, directly managing the hardware. Obviously, this design gives you more performance as you need less switches between user mode and kernel mode. It's also not as good for reliability, because if one of those operating system services crashes, then potentially the whole system crashes with it. The second design is the microkernel. Technically, in this design, you want as little services as possible to use kernel mode, and every other operating system services to use user mode. This means that non-essential services will run in user mode, like application IPC or device driver or the file server. And if one of those services crashes, then it can be restarted without crashing the full system. So this design is very good for reliability, because services can crash and be restarted. It's also easier to formalize, and security is usually easier to reason about in this kind of designs. But it's not as good for performance, because this design will incur a lot more mode switches between user mode and kernel mode, because in kernel mode only the basic IPC, virtual memory, and scheduling functionality are accessible, so one of those components might do multiple mode switches before they can return to the application. So as you can see, the examples are quite old, Munich or Mac, and no real current operating system uses this design for the performance drawbacks. Modern kernels usually have an hybrid approach that sits between monolithic and microkernels, which means that performance critical services will be inside kernel mode, and other services less critical will be in user mode. So for instance, the file server will be in user mode, while device drivers and application IPC will be in kernel mode, because these are frequently accessed, and having too many mode switches can be avoided by this design. So depending on how they are in the spectrum of monolithic and micro, the performance and reliability trade-offs are on the spectrum between both designs. So the examples of these designs include NT, the modern Windows kernel. And finally, a more recent design is the unikernel, where basically everything lives in kernel mode, even the applications. So boundary between the application and the operating system is very thin, because every single services live in the same address space, and the application can directly address and run operating system functions from the same context. So usually this design is when an operating system is really tailored for one particular application. So this gives you a lot of performance, because you no longer have any mode switches. And this is very suitable if you have one application in mind and want to deploy dedicated kernel in a virtual machine, for instance. The drawbacks are that this creates a single-purpose operating system, which is very specialized for that one application, which means it's not usable by more than these applications. So this summarizes our different kernel designs: the monolithic, the microkernel, the hybrid kernel, and the unikernel. As you can see, the boundary between kernel mode and user mode varies a lot between these different designs. So now this brings us to the notion of privilege levels, which determine what a piece of code can do on a system. So your CPU have different privilege levels, and depending on the current privilege level, you are allowed to execute some instructions and not other restricted instructions. So for instance, in user mode, you don't have any access to the hardware. This mode is typically used by applications. You have the supervisor mode, where you have access to some privileged instructions. You can manage registers and also the hardware. This is used by the kernel. And you also have the hypervisor mode, so you have additional access to virtualization specific instructions. So this is used by the hypervisor, which is a specific OS that can run virtual machines. Switching between these different privilege levels requires the use of specific instructions. And to communicate across the stack, so to switch from user to supervisor, you can invoke a system call, and to switch from supervisor to hypervisor, you can have an hypercall. So now we will focus a bit more on the notion of system calls. So system calls are essentially the way for application to execute privileged functionality that they don't have access to by going back to the kernel mode. This can include performing I/O, so communicating with the network or writing on disk. Can be resource management, so management of threads or memory. Communications, so sending signals or inter-process communications to other threads and processes on the system, or accessing basically any specific hardware. There are specific APIs in the kernel for the user application to perform all of these functionalities, and here we will focus on the way Linux does it. So now let's talk about the system call wrappers. So as a programmer, you will rarely use directly system calls. Usually you will rely on the libc functions that perform the system calls for you. So for instance, the write function is not an actual system call, it's a wrapper from the libc. It will perform additional checks before running the actual system call to the operating system. The wrappers can do some argument check, they can also handle errors for you with the kernel interface. Some may actually do more. So for instance, when you do memory allocation, if you have previously freed some memory, then the wrapper might actually be able to reuse this memory for the new allocation. This way it can completely avoid the system call and only perform the reallocation of the memory in user space without going again through the kernel and incurring a mod switch. Alright, now let's see how the hardware can actually implement system calls. The first way is through the use of software interrupts. Let me walk you through an example to explain to you how this works. So in this way, the user space software will place the system call number in a specific register. Then they will place all the arguments according to the ABI. We'll see what this means later on in different other registers. It will then trigger a specific interrupt for system calls. Then the hardware will spin the correct interrupt handler for system calls, and this handler will look through the table of all existing system calls and match the one that was invoked by index to retrieve the specific system call function. Then it will actually execute this function, and after that the result can be sent back to user space. Okay, now let's see second way that the hardware can implement system calls, and this is through the use of specific instructions. So some architectures provide specific instruction, syscall, svc, sysenter, to trigger the system call. But the way it works is that the user mode will still place the system call number in a specific register, and then it will also place the different arguments in different other registers, and it will use the syscall instruction. Now this syscall instruction will directly match the system call number to all other system calls they can find in the syscall table to retrieve the pointer to the system call handler, and then it will execute the function. And finally, the result can return to user space. So using specific instructions, as you can see, one level of indirection was avoided as the specific instruction enabled the hardware to directly look up in the syscall table for the right syscall to perform. The application binary interface I mentioned before, the ABI, is kind of analogous to an API. An API is the high-level interface for programmers, so for instance functions, prototypes, or data types. The ABI is the low-level interface for the compiler and operating systems. So this means all the calling conventions between the operating system and the hardware. So as you can see, different architectures like ARM, RISC-V, or x86 will use different registers to populate the syscall number. Also different other register where to expect the return value of the syscall and where to put the different arguments of the syscall. As you can note, Linux allows only 6 arguments at most for system calls. You can find more examples at man syscall. And on a second note, since most programmers will use the libc wrappers, then it means that conforming to the ABI is actually the job of the libc. So this is another perk of using libc, is that you don't have to change the ABI conventions based on the target architecture. Now this concludes today's lecture, and now you have 4 tasks that await you for this week. The first 2 tasks are training exercises. The first one is how to invoke a system call with the syscall libc function, so how to use the wrapper essentially. The second one is how to invoke the same system call in assembly, so without using the wrapper. And then you have main exercise, which is basically implementing a system call tracer, so a program that will snoop on every system call invoked. And then, if you wish, there is an optional exercise that is not created, where you can implement a new system call in the Linux kernel. And now some tips for the exercises. So for the training exercises, you will need to hijack some system calls, and for that you can use the environment variable ld preload, which basically lets you intercept shed libraries. This is useful because the libc wrappers for system calls are dynamically resolved through the linker. So if you override the linker, you can actually spin your own wrapper without changing the application code. And now another tip for the main exercise, you basically need to implement a system called tracer, which basically does the same thing as strace. So strace is a tool for tracing system calls that relies on the ptrace system call, and that lets one trace every system calls when running a program. So as you can see in the following example invocation of strace, it is set to trace multiple system calls for the invocation of echo foobar. And as you can see on the output, it was able to trace multiple system calls, for instance the BRK syscall, the read syscall, and also the final write syscall that writes foobar on standard output. Alright, this is all for today, and see you at the Q&A on Thursday.